And basically what we're up to today is we're going to talk about computed radiography, but I want to skim through Chapter 14, Computers and Medical Imaging, just so we have some shared terminology before we jump into the computed radiography thing. And I want you to be aware of the small parts of Chapter 14 that are important. There's not a lot, there's just a little bit. And then at the end I've got an activity for us because, to be frank with you, Chapter 15, all this digital stuff in Bouchon is the reason why I'm getting rid of this textbook. Like, this class next year will not be using this textbook. Foundations will not be using this textbook. I've decided to throw out this entire Bouchon textbook and move to a different text. It's the text that you'll be using for digital imaging. You don't have to purchase a new textbook, but I've found what I feel like is a better text. And one of the weakest parts of Bouchon is his discussion of computed radiography, digital radiography, and all that kind of stuff. He skims the surface of it a lot. And even this chapter, if you understand computed radiography, there's a lot of stuff that it's like, why didn't he talk about that more or whatever? So I've got an activity at the end of the day that's going to hopefully push us in a little bit deeper into this chapter, because there is some stuff hidden in this chapter that's super important, right? But again, he just kind of skims over it. And so I want to make sure, the reason why I put this lecture together is to make sure that we understand kind of some basic terms and have an understanding of it now, because it's going to affect image eval in the summer. And this stuff isn't going away. We'll come back to it in digital imaging right before you graduate. So we'll go to a little bit more depth then. But the big thing, really the biggest part of Chapter 14, the only thing that I found was not completely obvious or whatever, is his discussion of binary notation. It is helpful to understand what binary means. So it's on pages 270 and 271 in the textbook. And I'll tell you that basically binary, who here knows what binary means? Does anyone know what binary is?
It's ones and zeros, right?
Ones and zeros, yeah. Ones and zeros. And so we call this a base 2 number system, right? Like the number system that we use as human beings or whatever typically is base 10, right? Because I've got 10 fingers on my hand, and so we tend to think about things in tens or hundreds, or you know what I mean, like $20 bills, $10 bills, $100 bills, $50 bills. That's all base 10, right? Base 2 is just ones and zeros, and the way that it's thought about is powers of 2. So that's 2 to the n is what I've written up there. Everything in binary is some 2 to some exponential number. So like I think last week we talked a little bit about this in CT. I said the most common CT matrix size. Does anyone remember what that is? Most common CT matrix size? It's 512 by 512. Right? This number wasn't just like magically arrived at. I think it's 2 to the 8th. Don't quote me on that offhand, but I'm pretty sure that's 2 to the 8th power, right? So it is binary. The matrix sizes are all binary. So one sheet, like if you were ever asked about matrix sizes for digital imaging, which is a pretty common registry test question, you can just know if it's not if it's an odd number, we know for sure that's not right, because it couldn't be a simple binary expression. It's always going to be 2 to some power, right? So our computed radiography matrix sizes and receptor sizes and all the ways that the computer understands it are going to be based on binary. It will always be described as in binary units. And the only other thing that I would pull out of Chapter 14 is understanding what a kilobyte is. Kilobyte. And the reason I pull it out is because it's really important to understand that this prefix kilo, even though we use it sometime in the metric system, like kilometer or kilovolt peak, right, for kVp, this is not a metric expression. Like, a kilobyte is not metric. And the reason why it's not metric is because, again, it's in base 2, So the 1 kilobyte is equal to 1024 bytes, and again, that's, I think, 2 to the 10th power, or 2 to the, it's 2 to the 10th or 2 to the, what is it? 2 to the 10th. So this is 2 to the 10th power. So again, I just want to stress that when we talk about kilobytes, terabytes, gigabytes, all those different sizes for memory or for storage space or whatever, we're still working in base 2. We're not working in base 10. So don't trip yourself up and think that a kilobyte is 1,000 bytes. It's not. It's a little bit more than that, right? Or whatever it might seem to be from the metric system. So that's really the only important parts of chapter 14, is just understanding that binary is in base 2, and that because of that, all these binary expressions like terabytes, gigabytes, kilobytes, they are also pulled out of base 2, and this affects how our matrix sizes work. Let's jump into chapter 15, and one of the very first things that he talks about is photostimulable luminescence, and he makes a distinction between luminescence and like phosphorescence and things like that. And largely the way luminescence works is it has to be stimulated in order to emit light. So we're gonna exploit that in computed radiography. We're gonna work a lot with barium fluorohalide, and I meant to look this up, but I don't think he actually has the correct terminology for, it says barium fluorohalide with europium, but then he says BAFBREU. Do you see that? It's right below. The way he abbreviates barium fluorohalide is BAFBR. I don't think that's correct. I think that's barium fluorobromide. I haven't had a chance to look that up, but I don't remember what. I don't have a periodic table in front of me, but I'm pretty sure that's not the correct expression of barium fluorohalide. I just didn't have a chance to look it up. So if anyone can look that up on their phone, that'd be helpful to know. The significant thing about this is that this is a phosphor that's going to be inside of these computed radiography cassettes, and it's doped with europium, so it always have EU out here next to it. And the europium is really an important part of it. It works to capture the latent image. So what happens is the barium, when it's hit by the X-ray, the barium fluorohalide fluoresces slightly. And in that process of fluorescing, it causes the europium to become metastable. So it actually ionizes the europium. The fluorescence ionizes the europium, and it's going to eject an electron, and it's just going to sit there in a metastable state, right? And basically what happens is we then scan it with a laser, and the laser excites that and causes it to luminesce, right? That's the basic process of computer radiography. Everything he's driving at in this chapter is trying to unpack how that occurs, okay? So some key terms with that are going to be understanding luminescence, frankly, versus phosphorescence. What we're talking about is luminescence, which means that we have to hit it with a light, and then it's going to emit a different colored light. And that this europium is critical to it. That the europium is going to wind up in a metastable state when it's hit by the X-ray, and then when we hit it with a laser, it's going to, that electron will return to the europium and emit light. The light that's emitted by these crystals, we use a term turbid, right? And the way that you can think about turbid is that it's going to scatter. So, and that seems kind of apparent when I look at this picture here, because I have this phosphor layer, right, like these crystals here. And if you can imagine these crystals being just like the crystals in a diamond ring or something, if light was emitted right here inside this crystal, just like what would happen with a diamond ring, it can refract, right? It can go off in different angles. So the light itself might scatter slightly as it's being emitted, and we call that property turbid or turbidity, right? It's not a good thing. We don't want that. So one of the things that he looks at very briefly is he compares this conventional PSP plate with one that has he calls it a needle PSP. He doesn't really tell us why they started engineering these needle PSPs, but the reason that they did that, and I'll illustrate this real briefly here. So this one here that's illustrated in this diagram is a conventional one. The needle one would look very similar in that it would have a base, but then the crystals would all be lined up like this. And the reason that they design them like this, again, is this is going to decrease that turbidity. Because now when the light is emitted, it's just going to be emitted in one direction. It's going to have to follow those needle channels and go straight up back towards the place it's being read. Okay, so hopefully would give us a little bit clearer picture. Moving along here. Oh, one other thing I wanna look at is down here. This is kind of important stuff too. So the main significant thing here is so within the PSP, the main thing that we've got is these what we will call SPSs, right? That there are these storage phosphor screens, right? This section here we're going to call an SPS. I know it's kind of confusing, but this section right here is a storage phosphor screen. So that's the main chunk in terms of the thickness of what's inside of a CR cassette. So inside this, there's actually a cassette housing that's just plastic housing, right? And then we have all of this stuff. This is what actually is pulled out and read. Okay. In addition to that, though, and the thing that probably is giving it most of its weight is in the back of the cassette. There's lead. So if I were to ask why is a CR cassette heavy, well, there's lead in it, right? Why is there lead in it? Well, it's to prevent backscatter radiation. The fact that there's lead in it is also the reason why you never, ever, ever put a CR cassette in upside down, because essentially I've just put lead over the area that you won't see anything. I mean, the other reason that a lot of times lead is added to this stuff is because this stuff is very reactive to any kind of scatter radiation. So there's some kind of fog that winds up on our computed radiography cassettes, because this barium fluorohalide is very sensitive, and so if we haven't used a cassette for a day or two, it's best to erase it before we go out and do a portable with it, because they're very, very sensitive. They're about 10 times more sensitive to radiation than film. So they're very sensitive, and so we add this lead base to it. Also below that, there's a reflective layer and an anti-static layer. The anti-static layer is there because we're going to have to slip this cassette out of we're going to have to slip this PSP out of the cassette in order to read it. And so in the course of slipping the cassette out of the PSP out of the cassette, we don't want to produce static, because static would produce an artifact on our image. Okay? Okay. So it is important to be able to unpack the different kinds of noise that can be produced in reading. So I've already mentioned how these things have an anti-static plate on them to reduce image noise from static. But we can, so it's very rare to have any kind of static problem with these devices. But some of the device problems that we could have would be mechanical defects, and largely I would think about like a slow scan driver or the fast scan. He doesn't really talk about this in depth, but slow scan is the direction in which the image plate is fed through the reader. So typically it's the long axis of the image. It's going to be in the direction of the long axis. So this might be our slow scan direction, right? Then there's a laser that's very quickly going to go over this thing while it's being fed through the reader. And so the laser is going to go back and forth, and this back and forth of the laser we'll call the fast scan direction. So if you can imagine, it's slowly being fed through the reader while the laser very quickly moves across and is assisting with the reading. So any problem with either the laser or the motors that are powering the CR cassette can cause noise. There could be optical defects that relate to the intensity of the laser or the size of the laser. We've also talked about how this turbidity of the turbidity of the crystal could cause scatter. There can be problems with the way the light is actually emitted or collected from the crystal during the collection process, and then of course any kind of electronic noise and an adequate sample and adequate quantization. All those things would lead, this stuff here in particular would lead to what we call quantum model. And I think we've talked about quantum model some, but it means we just don't have enough signal to produce an image. And so we're going to have, the picture is going to look kind of grainy. Yeah, those are the primary things that we need to think about in terms of noise. So let's talk a little bit about how this process actually works in terms of reading. Initially what we have is, our CR cassette, and we expose it to some x-rays, and like I said, it will cause the barium fluorohalide to luminesce slightly, but the large thing that's going to do is that europium is going to become metastable. Okay? And so there'll be some light emission that occurs inside the PSP, but the main thing that's happening is that electrons are being ejected from the europium, and they're just sitting there. They're just sitting there in that phosphor plate. Now we're going to scan it with a laser, and it's really important to understand how the laser works. This is infrared light. So here on this illustration, it's illustrated as red, but it is infrared. And that's really important, and it's going to be a single color, typically red, but like a single kind of red. It's not a spectrum of red. It's like a single kind of red, and I can't stress that enough. And it's also going to be very, very small. It's important that because the smaller the laser beam diameter, the higher the spatial resolution will be for what we're reading. So the smaller the laser diameter, the higher the spatial resolution will be. And that's actually there on page 288, where it talks about the significance of the laser being really small. So when the laser has scanned over any of these europium atoms, the electron then returns to the europium and it emits light. It's going to emit a spectrum of light, and it's blue. The light is blue. So I don't know if that's apparent in this illustration here, but the light that it's giving off is going to be a spectrum of blue. So I said it's a very specific red light, and then a spectrum of blue is emitted by the europium as it goes from a metastable state to a stable state. And there's a really important illustration of this on the top of page 288. There's an illustration of this kind of spectrum, a discrete laser, and then a continuous spectrum of blue light. This is significant. He doesn't really tell us why it's significant, but let me draw this out here real quickly. So we got a spectrum of energies. We've got this blue kind of discrete spectrum, and then if you're looking at the color wheel, from blue it goes to like green to yellow to orange to red, right? And so this is very, very important from the computer's point of view. The importance of this is that there's a gap here, right? There's a gap between the spectrum of blue energies and then the very specific color of red that the laser is. And the reason why this gap is important is because we're trying to sample light, right? That's the way that we're reading this thing, is we're sampling light. So it would not work if I'm sampling red as well as blue. I wouldn't get anything. I'd get a very weird looking picture. So I'm only going to sample the blue. I'm going to have a laser that's scanning across it that's red, but then the computer only wants to look at the blue light. And that's helpful because there's a gap, even just on the electromagnetic spectrum, there's a gap between blue and red. So that's important, that as this thing is reading, that it recognizes, okay, that's the laser and that's the thing I'm actually trying to sample. Any process of receiving kind of analog signals for storage and analysis, we will call that signal sampling. Okay? Signal sampling is the process of receiving analog information or analog signals for storage and for processing. So the light that's emitted by the crystal is an analog signal. It's light, right? We're going to digitize that. And so it's then, the light is emitted and it's picked up by like might be called a photodiode or a PMT, a photomultiplier tube. It's a large glass optic piece that is able to amplify the light signal, that blue light signal, and feed it into a photodiode. What's the importance of that? It's amplified the signal, right? It's going to amplify that signal because it's a very weak signal. And in order for us to sample it, we're going to need to boost the sample up. We're going to boost the gain on it, if you will. That will increase noise, but it will also increase the signal, and that's what we're going to then digitize. Okay? So this part here, light emission, where it says light emission, really what we're doing is sampling it. We're taking this light, we're putting it through a photomultiplier tube, and then we're going to digitize that. So just like in CT scanning, where there's that ADC, the analog to digital converter, this has an analog to digital converter too. It's going to take that analog signal that it sampled and it's going to quantize it. Quantization, it sounds like a made-up word. It's a real thing. What it means is it's going to assign it a pixel value. So quantization means it takes that analog signal and it assigns it a pixel value. Quantization is what the analog to digital converter does. The ADC takes that analog signal, quantizes it, or assigns it a specific pixel value. He slips this in real, just to backpedal just a little bit. I may have skimmed over the stimulating laser just a little too quickly, but there's two basic types of lasers that are out there. Both of them emit some kind of red light. There's either, I think it's a helium, it's Hene, and I can't remember what that is on the periodic table, but like a helium nitrogen. I don't think that's nitrogen. I can't remember what it is. That's one type of laser. That's the older school laser. Most of what we use now is solid state. That's why I can't remember the Hene. So again, the X-rays cause this metastability inside the photostimulable phosphor. We scan that with a laser. It emits light. That light is picked up by a photomultiplier and digitized. Okay? The final step of CR, and it's the part that you are able to see if you're standing there by the CR reader, is this erasure phase. So it's going to turn on some very intense white light, and that white light is going to cause, if there's any electron that's hanging out there, if there's any europium that's still in a metastable state, this exposure to intense light will cause it to completely be erased. Okay? So that is the final process, and it's best to use these image plates as soon as possible after this erasure thing, because again, they are very sensitive. to radiation. The final thing, and he really doesn't talk about this at all, but it's here, it's latent in the text. He's kind of hinting at it in a number of ways. But if you look at page 290, where he's got this illustration that looks like this, and I'll draw it up here, but it's figure 1516. He has an illustration that looks like this. Okay? This is a graph of what the computer sees, right? It just gets like a straight set of numbers, right? This is what a discrete sample would look like. This is not really helpful because this image would be very, very flat. There would be an equal number of whites and blacks on the image. Like it would be uniformly gray, right? It would be a uniformly gray image. The lookup table then artificially creates contrast. And so we talked a little bit about this last week when I said that the creation of contrast in digital radiography is no longer specifically tied to KVP, right? It's tied to some computer processes. And one of the primary things that drives the visible contrast on our images now is this thing, the LUT. It means lookup table. Lookup table. The Fuji CR reader that we have in our lab has a lookup table, and you've used the lookup table now probably about 100 times, every single one of you, without even realizing that you were using a lookup table. But every time you tell the machine, so you took a hand x-ray, every time you tell the machine, this is a hand x-ray, the machine is thinking, okay, what's the lookup table for a hand x-ray? So it doesn't look at it like this graph here. This is just an illustration that we can understand. It looks at it as a series of numbers. It's a matrix of numbers, right? Sometimes this is called a kernel, like in CT that we call it kerneling. But so it has a matrix of numbers that it would expect to see on a hand x-ray. So every hand x-ray is going to have the same kind of expectation to it. It's going to have the same kind of histogram shape, right? Every hand x-ray, regardless of if it's overexposed or underexposed, centered correctly or not centered correctly, collimated correctly or not collimated correctly, it will have this signature histogram. The lookup table then takes that and applies it to what you got, and it's going to enhance the contrast. So the lookup table is the primary control of contrast now for digital imaging. The lookup table is the primary control of contrast. And the way it does it is essentially like this. Y'all remember that H&D curve that we looked at? It's going to apply an H&D curve to what you got, right? So for example, on this illustration here, I took this from another textbook, but this line here is probably what we got. This line A is what we got. Depending on the amount of contrast we might want to see, it might use a lookup table that will produce something like line E. If we're doing something like a chest x-ray, it might apply line E because that pulls the contrast out. Or line L if we need a high contrast image. If we want a short width, we're going to use a steep slope like what L has. It has a very steep slope. So this is going to give us a high contrast, right? So these lookup tables are very significant, right? They can even do weird things. So they're the primary control for contrast, but that's not all they do. Like if you look at, for example, this line M here, can anyone take a wild guess? What might line M do? Sometimes it's called black bone, but if you've ever been playing around in fluoro and they switched everything around, right, to where the bone is now black, right, and the air is now white, that's what this lookup table direction would do. It would switch everything around. It would flip the whole image inside out. So we primarily use them for the control of contrast, but they can also do things like black bone. The last two things I'll talk about real quick is top of page 291. He has an experiment that he's done, and he shows how a film screen radiograph looks. So it's a series of exposures of a knee x-ray. It looks like this, Hunter. A series of exposures of a knee x-ray. You can see the film goes from completely white to something that's almost starting to get burned out, right? Then he did the same, I think the same techniques or similar kind of changes in techniques with a computed system. Nothing changed, right? That is really the power of computed radiography, that as long as you're sending a signal, it can receive it, right? So one of the big takeaways here in this chapter to that point is on page 292, the final penguin box. He says, computed radiography should be performed at lower techniques than film screen radiography. Well, what's he talking about? The way that some other writers have argued is that there could be across the board, a 15% increase in KVP. Now, he's just said that there could be lower techniques than film screen. But the way that we're talking about that now is a 15% increase across the board in KVP. How is that a lower technique? There you go. That's it exactly. So that 15% increase is going to allow me to decrease my mass by what? Half. So the promise of computed radiography is that we can use increased KVP, because KVP no longer controls contrast, the lookup table does. And because we're using a higher KVP, we can knock our mass in half. Now, there was a really botched rollout on that, I'll tell you that right now. Because I was kind of front lines when these decisions were being made, and it was not communicated very well. So this is still something that we are dealing with in our departments to this day, techs not understanding that very basic principle that we can increase our KVP in order to decrease our mass. In fact, if you've ever worked with some of these older techs and asked them about the KVP they might use for something, chances are they're going to tell you something that's much lower than what is in your Merrills, right? Why is that? Well, it's in your Merrills now, but again, it was never completely adequately communicated to the people out in the workforce. Okay, that is it for the